Now we're going to consider our vector spaces over F, which will be the reals of the complex. And some constructions will also work over the quaternions, but we must bear in mind that the quaternions are not commutative. So sometimes constructions use the commutativity of the reals or the complexes and then are not available for quaternionic vector bundles. So let's recall from way back when in our discussion of bundle basics, what does this mean? So we have local trivializations over some coordinate patch to u alpha times Fn. The n here is equal to the rank of our vector bundle, which I'll usually denote by E. And so if I denote x and then v, say some alpha, as a point in u alpha times Fn, and our transition functions are phi beta phi alpha, take v alpha to x v beta, with v beta equals g beta alpha of x dot v alpha, then what we're saying is that g beta alpha goes from the overlap to the general linear group over the reals complex of quaternions. And this is just the usual linear action on Fn. Okay, so examples. A vector space is a vector bundle over a point. A second example is the Mobius bundle, where we take the circle and we take our usual coordinate patches, u plus and u minus, and we take the element of the general linear group, which is 1 here and minus 1 here, and the vector space is just a real line. So that's the Mobius bundle. And then a third example would be M is any manifold, then the tangent bundle of that manifold is a good example of a vector bundle. So now we can talk about maps between vector bundles. Those are bundle maps, which in the present context means that we have a vector space. We have a vector space, say, E sub x over x, and if we had another bundle, E prime, y over y, then a bundle map would be a map which, when restricted to these fibers, is a linear map between the fibers. So we can talk about isomorphisms of vector bundles. Those will be families of isomorphisms between these vector spaces. And so we can discuss isomorphic vector bundles. A bundle is trivializable if there exists an isomorphism to m times Fn that is equal to the trivial bundle of rank n. And of course, we should, as I've stressed many, many times, we should just distinguish between a trivializable and trivialized. A trivialized means that we actually choose an isomorphism to f times Fn, and these bundles have automorphisms. The automorphisms of the trivial bundle is equal to a torsor for the group of maps from M into the group G, L, and F. So that's usually an infinite dimensional group. And trivializations can differ by elements of that group. I also should stress that it's important to be clear about the difference between real and complex vector bundles. And in my group theory course, I always hand out a little sheet of how you just talk about complex structures on a real vector space. You can take a complex vector space and regard it as a real bundle, and then you can make that, again, a complex bundle, and so on. There's a whole story with real, complex, and quaternionic vector spaces, and that all generalizes pretty much word for word to bundles. So I'll assume you know all that. And another piece of terminology is that a one-dimensional bundle is called a line bundle. Now you have to be careful. That can mean two different things depending on whether you're talking about real or complex. So if you're talking about a real vector bundle, a line bundle is a bundle whose fiber is isomorphic as a vector space to R. And if you're talking about a complex line bundle, the fiber is isomorphic as a complex vector space to C, which is a two-dimensional real vector space. Okay, I'll come back to line bundles later. They play a distinguished role in many constructions. Okay, now I didn't say much about the nature of this map here, and the nature of the transition functions determines different categories of vector bundles. So E is continuous or smooth if the G beta alpha of x's are continuous or smooth. So what I mean is that if I have a smooth vector bundle, that means that there exist trivializations such that the G beta alpha are smooth. Now I could do something stupid. I could choose a stupid trivialization which is, let's say, continuous but not smooth. That's just, then I just chose a stupid trivialization. What we say when we have a smooth vector bundle is that there exist trivializations such that the G beta alphas are smooth. Now this issue becomes a little more serious when we have a vector bundle E over M, where M is a complex manifold. Okay, because by definition, on a complex manifold, we have coordinate patches which map U alpha into some open region in complex number space. And so U alpha beta goes into some complex region in complex number space. And then we can say a holomorphic vector bundle is one such that there exist trivializations so that the G beta alphas, which now go from, let's say, CD into GL and C, are holomorphic. Okay, so first of all, you see, it wouldn't make sense to talk about a holomorphic real vector bundle. You need the GL and C here so that your transition functions are holomorphic maps of this complex manifold into this complex manifold. Okay. Now let's talk a little bit about sections of vector bundles. Well, as with the general notion of a fiber bundle, a section of a vector bundle E over M is a map M to E, so that we have a left, a right inverse of the projection. Okay, so what that means is I mean, we're always assuming that we're talking about continuous at the very minimum. So a section means that we're making a continuous choice of a vector in the vector space E sub x. So another definition is that a local framing over U of E is a choice of n continuous, depending, or smooth, depending on our category, sections. Let's call them S sub 1 through S sub n. So these are sections of E restricted to U. My symbol for sections is capital gamma. Such that for each x in U, the S sub I of x provide a basis for the fiber E restricted to x. So, I'm giving a local framing over some patches U sub alpha. That's the same as to give a trivialization. So why is that? Why is that? Well, suppose that phi sub alpha from phi inverse of U alpha to U alpha times Fn is a trivialization. Then we could choose a basis. We could choose a basis of V sub I for Fn, and we could define S sub alpha I of x to be phi alpha inverse of x V sub I. So these V sub i's don't depend on x in any way. In general, these S sub alpha I depend on x because they're defined this way. Now, across patches, we'll have transition functions, as I've said before. So those transition functions will look something like this. X g beta alpha of x, upper j, lower I, of Vj, with sum on j, understood. And therefore, across patches, these local framings will look like this. G beta alpha x, upper j, lower I, sum on j. Now this is true in x and U alpha intersect U beta. So local framings exist over each patch, but there's no guarantee that if I have a local framing in patch beta, and then I make it agree to define a local framing on the overlap here, there's no guarantee that I can continue this local framing into the rest of U alpha and have it continue to be a framing. Namely, there's no guarantee that I can have it continue to provide a basis. Keyword there is basis. Anyway, given a local framing, any V in the fiber of E above x can be written as V as the sum of Ci of x, S alpha I of x, where the Ci of x's are in F. So these are just honest functions. And so when I say a section is continuous or smooth, what I mean is we choose local framings such that these G beta alphas are smooth or continuous or holomorphic. And then we require the same things to be true of the CIX with respect to that basis. Okay, now conversely, so I've shown that given given a local trivialization, I can make a local framing. Conversely, given a local framing, we can define local trivializations. That's probably pretty obvious to you, and the details are in the notes. Now, local framings exist because local trivializations exist. A global framing is a choice of n sections such that they form a basis for the fiber above every point. And those need not exist. So a global framing would be a choice of sections Sn and now gamma of E, which form a basis for all E sub x's. And these need not exist. In fact, if you have a global framing, that's the same thing as getting a trivialization of your vector bundle. Okay, so an example of this is a Lie group. So if G is a Lie group, then the tangent bundle to G is trivializable. And indeed, a global framing is provided by the canonical left or right invariant vector fields psi of t, where t runs over the Lie algebra of the Lie group. That's, again, something I described in my group theory course. I'm not going to take time to explain that in detail, but if you know about Lie groups, you understand what I'm talking about. Okay, now because we have this linearity here, the space of sections let's call it gamma of M with values in E. Sometimes I abbreviate that as gamma of E. I probably should have written gamma of M with values in E. Has some extra structure. Okay, so first of all, we can add sections. We can take two sections, S1 and S2, and we can add them because their values for each x is in a vector space. And by the same token, we can multiply them by scalars. So gamma of ME is a vector space itself. Okay? Now, if the dimension of M is positive, and we're talking about continuous or smooth sections, then it's an infinite dimensional vector space. So take a moment to contrast that with the case of principal bundles. Remember, we proved that if there was a global section of a principal bundle, then it was trivializable. Right? But it's quite different for vector bundles. You see, a vector bundle always admits at least one canonical global section. What is it?
Zero section.
Zero section, right. You see, let me say what a global section looks like in terms of framing. So,
Excuse me.
yep.
Does this contradict with the H0 I thought this gamma is
I'm coming to that in a second. But no, because I'm talking about, I think I know what you're thinking of, and I'll discuss it in a second. But I'm talking about continuous or smooth sections. And you're probably thinking about holomorphic sections, because you live in the holomorphic world. But but the holomorphic world is a subset of the bigger world. So you see, going back here to these local framings, you see, if I have a vector, it doesn't. The vector in the vector bundle doesn't care about a particular choice of framing. So there are different coefficient functions relative to the different choices of local framings. So if I had a global section, v of x, then that would be tantamount to giving tuples of functions on each patch which satisfy overlaps. And I have an exercise in the notes where you show that the overlap conditions would look something like this: G beta alpha of x, J I, C alpha I of x. So this is a global section. So if you think about your vector bundle in terms of transition functions, then a global section would be a choice of tuples of functions, C alpha I of x, in each coordinate patch, which are related on patch overlaps by this linear transformation. So again, as I said before, if we're talking about continuous sections, then the G alpha beta of x's are continuous functions. And then we would require that these be continuous functions. These are smooth, and these should be smooth. If we're in the holomorphic category, so then the G alpha beta of x's are holomorphic functions on CD, and then we would require for a holomorphic section that the C's be holomorphic. Okay? Now you can see that a trivial solution of this is to put the C's all equal to 0. Okay? So there's always the 0 section. But by partitions of unity, using an argument we'll see a little bit later, you can show that there are plenty of sections, continuous and smooth sections. So this is, in general, an infinite dimensional vector space. Now, as Ben was alluding to, if E is a holomorphic vector bundle, and M is a compact, that's important, compact complex manifold, then the space of holomorphic sections, which is denoted H naught of M with respect to E, tends to be is a finite dimensional vector space. And the reason it's so different is that what you're really talking about when you're talking about holomorphic sections is you're really talking about solutions to elliptic partial differential equations. Something like d bar is s equals 0. And so that's really a different kettle of fish. And so these, you can prove that when M is compact, this will be a finite dimensional vector space. Now, a little more is true here. There's a further algebraic structure, which is very interesting and which we'll talk about some more in some subsequent lectures, which is that going back to the continuous and smooth case, gamma of ME is a module over the algebra of, well, continuous or smooth functions on M. Okay. So recall, early in the course we talked about the importance of the algebra of functions on M. I talked about Gelfand's theorem, how you can reconstruct the manifold from the algebra of functions on M. So now I'm observing a little more the sections the vector space of sections of a vector bundle, in general an infinite dimensional vector space, is a module over the algebra, in general an infinite dimensional algebra, of functions on M. And now why is that? Because you see, if f is some function, globally well-defined function on the manifold M, valued in R, C, as is appropriate, then we can define f of x, say, on one of these local framings to be, this is the definition, phi alpha inverse of x comma f of x vi. Okay? And now, because scalars commute with matrix multiplication, that will make sense across patch boundaries. So I'm using exactly at this point that scalars commute with matrices. Scalar multiplication commutes with matrix multiplication. So I couldn't go and say that this is a module for the group of maps from M into G, L, N, F, where N is bigger than 1. I couldn't do that because matrices don't commute with matrices. But because functions commute with matrices, I can do that. And so it's well defined to say that f dot s is the new section f of x times s of x. Now, in general, about what we're going to prove later, this is something I'm definitely hoping to do before the semester ends, is to prove that gamma of ME is what's called a finitely generated projective module. Okay, more on that later. Okay, so now what I want to stress again, as I've said before, is that what we're doing is linear algebra in families. So for vector bundles, because the fibers are vector spaces, yes?
Sorry, I just had a small question
Yeah.
about something you
Yeah.
said earlier.
Yeah.
Is it true that if you use a trivial bundle, then there is a global framing?
Absolutely.
I was thinking if you have like S2,
Yeah.
and you consider the tangent bundle over that,
Yeah.
if you have a vector field on that that's continuous, it would be 0 at some point, wouldn't it?
Yeah, that's right. And you see the tangent bundle to S2 is not a trivial vector bundle.
Oh.
And you just gave a reason why it can't be.
Oh, I thought a trivial bundle was just a manifold. Oh,
So
okay.
what did you think a
I see.
trivial bundle was? A trivial bundle,
Okay.
still on the board. A trivial bundle, by definition, is f times, okay, in this case we're talking about a real vector bundle. So a trivial bundle, this is the trivial bundle.
Right. Okay.
Now, a trivialization would be a bundle map, psi, from the tangent space of S2 to that. But there is no such isomorphism of vector bundles. Okay. And you just gave a good reason why. If you chose, you see, what if you tried to choose global framing? So you try and choose some pair of linearly independent vectors, tangent vectors. Well, you know that one of them is going to go to 0 somewhere, by the theorem you just quoted. And there, exactly at that point, it fails to be a basis. I'll say some more about that kind of thing in a moment. Any other questions? All right, so I was stressing that what we're doing here is linear algebra in families. Okay, so you see these, well, we now have constructions. We have the way to do various constructions which are just not available for fiber bundles in general. So for example, if we have two vector bundles, E and F, then we can define the direct sum vector bundle whose fiber at x is E sub x direct sum f sub x. And you see, if the transition functions for E were some matrices G beta alpha, E of x in some trivialization, and we had G beta alpha f of x in some trivialization, then the transition functions for this guy would be block diagonal matrices like this. Okay? So those would be the transition functions of your direct sum vector bundle. By the same token, we can define the tensor product of vector bundles. Same story. So we take E sub x tensor f sub x. And then the x's varying continuously. Okay? And so the transition functions of this guy would be GE beta alpha of x. This is an n by n matrix if E is rank n. Tensor GF sub beta alpha of x. And this would be an m by m matrix if f were rank n. Okay? So we can go on. You know, anything you can do in linear algebra, you can now do for vector bundles. With a catch, a very important catch, which I'll mention in a second. So, okay, so we can talk about EF. Okay? We can talk about E dual. Right? The fibers of E dual are HOM of EX into F. We can talk about anti-symmetric tensor products, symmetric tensor products, and so on. We can also talk about subbundles. So if at every point f sub x is a subspace of E sub x, then we say that f is a subbundle of E. Similarly, we can talk about exact sequences of vector bundles. An exact sequence of vector bundles means that we have, at every x, these vector spaces with some linear transformations, iota sub x and pi sub x, such that the sequence is exact. Okay. And then we can talk about complexes. EI to EI plus 1 to EI minus 1 with linear transformations Ti minus 1, T sub I, and so on. And this would be a complex if the composition of these linear transformations is 0. And all of this can be done pointwise. This can be done for vector spaces, and therefore makes sense for vector bundles. Now, I said there was a catch to what I just said. I wonder if anybody saw it. Well, you see, what I said is true about any construction in linear algebra which is canonical. That is, basis independent. Okay? Because you see, in order to honestly do these constructions, you've got to choose local framings. And that involves some kind of choice of basis. Okay? And then there are different local framings, okay, which I can rotate these local framings locally. So if my construction depends on a choice of basis, that is, if it is not canonical, then the global statement might not be true. For example, every vector space has a basis. Not every vector bundle has a global framing. Right? So you can't necessarily conclude that things that are true at a point, for a vector bundle over a point is a vector space, you can't necessarily conclude that something which is true for a vector space is true in families. All right? So what's a good example of that? Well, I think you all know that the dual space of a vector space is isomorphic to V. Right? That's a famous example of a statement in linear algebra which is not a canonical statement. In order to write down an isomorphism between the dual space, of V into F and V, you need to choose a basis. But that involves choices. The choices can get screwed up by these transition functions, and so it might not be true. And indeed, in general, it might not be true when you try and go to families. In general, the dual vector bundle, which certainly exists, you see, the definition of VF, the dual space, that's a canonical thing. The isomorphism is what's not canonical. In general, the dual vector bundle is not isomorphic to E. In general, those are non-isomorphic vector bundles. Now, one thing that is canonical, that goes back in this list of things I can do for a vector space, and it's true in families, is that if V is a complex vector space, then there's a canonical vector space V bar, the complex conjugate of V. And what it is set-wise, they're the same. Every vector in V corresponds to a vector in V bar. I'll just give it a different name to distinguish it. The thing that makes V bar a different vector space from V is that the scalar multiplication on V bar is by definition taking the complex conjugate of the scalar multiplication on V. So we have the opposite scalar multiplication on V. Okay, now that's a canonical thing. You never saw me choose a basis to define that. And so therefore, if E is a complex vector bundle, then there's canonically defined another vector, complex vector bundle, E bar.
But that's not holomorphic.
If E were holomorphic, then E bar would be anti-holomorphic. So, for example, what are tensor fields? Tensor fields in general relativity are simply global sections of the tangent bundle to some power tensor the cotangent bundle to some other power. So in the language that we're using, that's what tensor fields are. Okay. And K and L are the number of covariant and contravariant indices. Now another linear algebra thing we might like to discuss is if V is a real vector space, then we can talk about orientation. Okay. So what is an orientation? Well, one way of thinking about orientation is that you think about the set of bases for V. So let V of V be the set of all bases for V. Okay? Nice canonical object. And now this is a torsor for GLNR if V has rank n. Remember what a torsor is. It's a principal homogeneous space. It means any two are related by an action of the group element. Okay? And there's no isotropy group at any point. So think about that. Any two bases of a vector space are related by a GLNR transformation. Okay? And if some group element in GLNR is not trivial, it's going to change the basis. Now, GLNR has two components. Has two connected components. So there's GLNR plus disjoint union GLNR minus. Okay, and this is the matrices with the determinant of A greater than 0. That's the connected component of the identity. So therefore, the set of all bases for V has two connected components. B1 disjoint B2. Notice I'm not calling it B plus and B minus. There's no sense to saying which one is plus and which one is minus. They're just two components. So an orientation on V is a choice of component. Okay, so that's an orientation on a vector space. So now we can try and talk about an orientation on a vector bundle is a choice of orientation on E restricted to U alpha. Let's assume that U alpha is connected, which is consistent across patch overlaps. So that means that the determinant of G beta alpha is positive on U alpha beta. Now, there can be obstructions to orientability. For example, the Mobius bundle is unorientable. So here's an example where we had to make a choice. We had to make a choice, and therefore it wasn't canonically, it wasn't guaranteed to exist globally, and indeed there can be obstructions globally. In fact, we can define mathematically an obstruction which is called the First-Stiefel-Whitney class. So you see the sign of the determinant of G beta alpha we could write as -1 to the, let's call it n beta alpha. I guess in the notes I call it omega beta alpha. Okay? Now this has to be locally constant, so omega beta alpha goes from U beta alpha to Z mod 2Z thought of additively. Okay. Now this is a check 1 cocycle, which means in this case that on trickle overlaps, okay, omega alpha beta plus omega beta gamma plus omega gamma alpha is 0. Everything is with coefficients mod 2. And so therefore, it defines a check cohomology class. Okay. Now, why talk about the cohomology class? Because you might say, well, okay, if this omega beta alpha is not 0 in some overlap, then you're dead, right? Wrong. Because, as we've seen in similar examples, you could still make changes of your choice of trivialization, right? So if you change the choice of orientation on U alpha, that amounts to a map lambda alpha from U alpha to Z2. And so if I make such a change of my choice of orientation on the different patches, then I'll get a new cocycle, which is the old one, plus lambda beta plus lambda alpha. Okay. Now, remember, I'm working with mod 2 coefficients, so this is the same, if you like, as this, which would be the right formula if I were thinking about cocycles over Z. And this doesn't change the cocycle relation. And so solutions of this equation, modulo these identifications, defines a cohomology class in check cohomology. And this is, by definition, the first Stiefel-Whitney class of E. Now, I talked about the first Stiefel-Whitney class of principal bundles, principal Z2 bundles, before, earlier in the course, and I'm going to relate those two concepts in a future lecture. Okay, so so this is the only obstruction to orientability, and therefore this is the only obstruction. And therefore, if M is simply connected, then all real bundles are orientable. Okay, so failure of orientability is a phenomenon of not being simply connected.
I'm sorry, did you prove this before? Or? I mean,
Well, I defined first Stiefel-Whitney class in a rather different way for principal Z2 bundles before.
no, but simply connecting is H1.
Oh, I certainly proved before that this is of pi 1m into Z2. So if it's simply connected, then. All right. Now, one thing to note is that all complex vector bundles are canonically oriented. Okay. So if I have Cn, it has a canonical orientation, and then on the patch boundaries, on the patch overlaps, we have a map from U beta alpha into GLNC. Now, if A plus IB, where A and B are the real parts, live in GLNC, then we can map that into GLNR this way. Now this matrix here, so this is in GL2NR, this matrix is similar to the matrix A plus IB, A minus IB, and therefore the determinant of A, B minus BA is equal to the determinant of A plus IB, absolute value squared, and it's positive. Okay? So, therefore, if we have any complex vector bundles, and we regard it as a real vector bundle, then it's canonically oriented. Okay, so we don't have to worry about that for complex vector bundles. Now, something that's very important to check here is that supposing I have a map M to M prime, and I have a vector bundle E prime over M prime, then I can talk about the pullback bundle of E prime. And I can talk about its first Stiefel-Whitney class, and I claim that that's the pullback of the first Stiefel-Whitney class of E prime. And so this is a crucial property of all characteristic classes, in particular of the first Stiefel-Whitney class, and this is called naturality. And if I get to talk about characteristic classes, we'll be going into that in much more detail. Okay. Now, I see time is marching on. Another important construction in linear algebra is that of taking the determinant of a vector space and the determinant of a linear operator between two a priori different vector spaces. This can also be generalized to bundles, defining something called the determinant line bundle. It's very important in the theory of anomalies, in the interpretation of quantum mechanical anomalies of chiral fermions. But I see that time is pressing, so I'm going to just skip over that. If you're interested, have a look at the notes. I want to say a little more about obstructions and characteristic classes. So how can we measure the amount, in quotes, by which a vector bundle is non-trivial, i.e. non-isomorphic to the trivial vector bundle? You see, the trivial or the trivializable vector bundle has a isomorphism to the trivial vector bundle. The trivial vector bundle is a global section. Well, we can try and form a global trivialization and see how much, the amount by which we fail. So try to make a global trivialization and ask by what amount, and that's very vague, but I'll make it precise, we fail. So let's begin with a real line bundle. L. And so we look at some section, S of x, which is a section of L. Well, this will be a global framing. This will be a framing. So S of x defines a framing if S of x is not 0. However, so what we're looking at is what's the 0 set of S? 0 of S equals the set of x such that S of x equals 0. Now you see, that equation doesn't care about what trivialization we're talking about. Okay? You change trivializations, doesn't matter. 0 goes to 0, because under change of trivialization, S just gets multiplied by an invertible transformation, which in this case is just an invertible real number. So this is a perfectly well-defined subspace. Okay? Now, in general, this is one real equation in D unknowns, where D is the dimension of M. Okay? So you think about choosing some coordinates for M. Okay? x1 through xd. Choose whatever local trivialization you want. So in that local trivialization, S looks just like a function of d variables. So you have one real equation on a function of d variables. And 0 set, in general, will be some dimension of m minus 1 dimensional 0 set. Okay? Now, if I start changing my section, if I start modifying my section, then the 0 set, of course, will change. It'll move around, but it'll move around continuously. So the homology class of 0 set of S is well defined. And independent of S. Generic choices of S. Of course, I could do something stupid. I could take S equals 0. Right. Then the whole manifold is a 0 set. That's not a generic section. I'm saying choose a generic one. So then what we can say is the first Stiefel-Whitney class is the Poincaré dual of this homology class. And one can show, I'm not going to show it now, but one can show that's the same as the first Stiefel-Whitney class I've defined over there. So I'm not going to show that, but let's look at some very simple example. Let's look at our Mobius bundle. Okay? And we'll think of the Mobius bundle as, so we have M over the circle. We'll think of the circle as the interval, 0 to 1, where we identify 0 is identified with 1. Okay? So let's think of the circle that way. And so then we can draw the Mobius bundle. We have 0 here and 1 here. We have the real line here. And we're identifying this real line with this real line here by taking y over here to minus y over there. Okay, so that's the Mobius bundle. So what is a global section? Well, a global section is some function s of x such that s of 0 is minus s of 1, and s is continuous, smooth, if you like. But continuous is the key property. Now, if I have a continuous function on 0 to 1, which has opposite sign on either end and is non-zero, as it is generically, you see I'm taking a generic section, then there have to be an odd number of zeros. Okay? And so what we're going to get is we're going to get a non-zero Poincaré dual. Now, I should have said, where is this Poincaré dual living? In general, the zero set of S, which is a dimension of M minus 1 dimensional subspace of M, is non-orientable, or unorientable. So we have to work in Z mod 2 homology. That is to say, when we were dealing with unorientable subspaces, you can't talk about homology with coefficients in Z, because to define homology and coefficients in Z, you have to choose oriented boundary. You have to talk about oriented chains. Okay, you usually formulate singular homology in terms of maps from simplices into your manifold. They have to be oriented if you're talking about homology with coefficients in Z. But if you don't worry about orientation, you can work with coefficients Z2. So Z2 homology always works without choices of orientation. In general, there's no way of pinning down the orientation of these spaces. And so you have to work in Z2 homology. And so the Poincaré dual works in Z2 homology. And so this is going to be coefficients in Z2. Okay, so I have 1 plus 1 plus 1 mod 2 is 1 mod 2. And so I have a non-zero Stiefel-Whitney class. And we see that that's an obstruction to a global framing of the Mobius bundle. Yes?
Question. When you say homology class of zeros, you mean the set of zeros defined up to smooth deformations of some generic?
What I'm saying is you choose a generic S, and you look at its zero set.
Right.
Okay? Okay, so that's some submanifold of this dimension. It defines a homology class with Z2 coefficients, because I haven't chosen an orientation. Okay? If I change my generic section to another generic section, You see, the space of all sections is a vector space. So I can connect any two sections by some path. Okay? And then my zero set will smoothly deform. And therefore, the homology class of that zero set will smoothly change. So the homology class is well defined. And therefore, so is its cohomological Poincare dual. So that's the Stiefel-Whitney class.
Question?
Yes, sir.
In this case, the zero set is points, and you're saying these points are not oriented.
That's right. The points are not oriented. So we're just doing mod 2 homology. So we're just counting. Now, let's do the same thing with a complex line bundle. Okay, so supposing now we have a complex line bundle. Okay, so now we'll have L over M, a complex line bundle. Now remember, that doesn't mean that M is complex. You need M to be complex for a holomorphic line bundle. I'm just talking about a complex line bundle over some general C infinity manifold. Okay? So the fibers are one-dimensional complex vector space. So now we can play the same game. So now the zero set of S is the set of X such that S of X equals 0. Once again, that's independent of how you, that zero set is independent of what trivialization you choose and so on. But if you choose a trivialization, then S of X equals 0 is two real equations in D variables. And using the fact that the complex vector bundle is orientable, you can show that zero set of S is orientable. So, the zero set of S, again, for generic sections, defines a homology class in H sub dimension of M minus 2 of M with now integer coefficients. And C1 of L is the Poincare dual of the zero set. And that's in H2 of M with Z coefficients. And I'll give you some examples of that later on. So let's try and generalize this idea. Supposing that E is an n-plane bundle. That's another name for a rank n vector bundle, n-plane bundle. So now S of X equals 0 is n equations. Right? Because in a local trivialization, S of X is going to have n components. So that's n equations. So that's n real equations for a real vector bundle, n complex equations for a complex vector bundle. Okay? Then, once again, the zero set of S has a Poincare dual, which is in H upper n, of X of M with Z2 coefficients. If we're talking about real vector bundles of real rank n, or in H upper 2n of M Z, if we're talking about complex rank n bundles. Okay, and this defines what is called the nth Stiefel-Whitney class or the nth Chern class of your vector bundle. Now what about the other Chern classes? Well, if we try to construct a field of K linearly independent sections, S1 through Sk, they're going to fail to be linearly independent. They fail to be linearly independent if there exist constants alpha 1 through alpha k such that alpha 1 S1 of x plus alpha k Sk of x is 0. So if we fixed the alphas, okay, and asked where does this happen, that would give us, for fixed alphas, that would give us a dimension of m minus n dimensional submanifold. However, we can vary the alphas in projective space of dimension k minus 1. Because after all, why projective space? Because this condition, you see, is invariant under rescaling the alphas by a non-zero constant. So the place where these will fail to be linearly independent, so S1 through Sk will fail to be linearly independent, on a submanifold of dimension m minus n plus k minus 1. And so the Poincaré dual will be either a Stiefel-Whitney class, Wk of E, in H n minus k plus 1 of m with Z2 coefficients, or Ck of E in H in 2n minus 2k plus 2 of m with Z coefficients. So that's just a sketch, very rapid sketch of the obstruction theory approach to characteristic classes. And it gives you a real feeling for what they're measuring, right? They're measuring obstructions to trying to find partial trivializations, fields of vectors which are not zero, or sets of vectors which are linearly independent. And the Chern classes, the Stiefel-Whitney classes, if non-zero, are a way of mathematically measuring the obstruction to being able to do that. All right, so if we get to it, there's another way of approaching characteristic classes, which is a little more systematic and I think a little formally a little easier to work with. There are actually two things you can do. So one thing you can do is you can use the universal bundle, which we are going to talk about, and the cohomology classes of classifying spaces. So you can sort of define universal Chern classes and Stiefel-Whitney classes. And another approach, which is what you'll usually find in physical applications, is called the Chern-Weil formulation, where in order to, what this is about is writing concrete formulas for the Chern classes, which uses an invariant polynomial on a Lie algebra and a connection on the vector bundle. Okay. And in terms of those two pieces of data, you can write down formulae for the Chern classes once you choose a connection. Now, there's a slight disadvantage to this, which is not usually such a big disadvantage in physics, but it does miss torsion. So in general, these cohomology groups, or these cohomology groups here, are finitely generated abelian groups. And so they can have torsion subgroups. And in the Chern-Weil formulation, you are working with connections, you're working over the real or complex numbers, and so you'll miss torsion in the characteristic classes. Oh boy, oh boy, oh boy. Let me just do a few quick things, more along the lines of this linear algebra and families. So another thing you do in linear algebra is you talk about quadratic forms and sesquilinear forms. Okay, so those make sense on vector spaces. So you can do it in families. And so you can do it in families, and you know, that generalizes in the obvious way. So for example, a quadratic form we could think of as a global section. There's a lot more details about this in the notes, but since I'm out of time, I'm going very rapidly here. So you can think of a quadratic form as a global section of E dual tensor E dual. That's a quadratic form on E. And then if you want it to be a symmetric quadratic form, well, it's a global section of the symmetric tensor product of E dual. And then if you ask that it's positive, that's what we would call a metric on E, then that makes sense globally. Similarly, a sesquilinear form would be a global section of E bar dual tensor E dual. So we know that there are lots and lots of these things because they're infinite dimension, because sections of vector bundles are infinite dimensional vector spaces. But if we put a condition like non-degeneracy or positivity, then it's not so obvious that they exist. We just saw obstructions to non-zero vectors and things like that. So here's a useful theorem. Any real vector bundle admits a positive metric and any complex vector bundle admits a positive Hermitian form. So how do we prove that? So we're going to use the positivity. So what we do is we choose charts with local trivializations. So this will go to some RD times Rn or Cn. I'll just do the real case, and the complex case is identical, really. And now we just pull back the standard Euclidean metric on Rn. Okay? So let's define G alpha to be G alpha on this local framing. Oops, that's the same alpha there. Is equal to delta Ij. Now, that looks silly, right? Because that's not going to. If I do that on patch alpha and I do that on patch beta, they're not going to agree with each other. I'm not going to get a globally well-defined object that way. But what I can do is I can introduce a partition of unity subordinate to my cover. So I take a partition of unity subordinate to u alpha. And so what is that? That's a collection of functions, lambda alpha, from u alpha to r plus. So they're non-negative functions. And the support of lambda alpha is sitting inside u alpha. Okay? And finally, the summation over alpha of lambda alpha of x is equal to 1 for all x in n. So the picture you should have is that, you know, here's your manifold, here's u alpha, here's u beta. We have some function, some real value, some non-negative function here. And so over u alpha, it looks maybe something like this. Goes down to 0. And then over u beta, it looks like this. So the support sits inside support of, this is lambda alpha, sits inside u alpha. Lambda beta sits inside u beta, but the sum is equal to 1. So now what I can do is I can take G and I can write the sum over lambda alpha, this G alpha. Okay, now this G alpha makes sense on the patch U alpha. It does not extend globally in any well-defined way, but that's okay because I'm multiplying it by this thing, lambda alpha, which vanishes outside U alpha. Okay. Now, at any x, there exists some lambda alpha, which is positive, because I sum to 1. Okay? So then that lambda alpha, G alpha, will be positive. Moreover, positive quadratic forms are convex. See, if I add two positive quadratic forms, it's again a positive quadratic form. So adding in all these other guys doesn't hurt. Okay, so that's the end of the proof. So, for example, if E is the tangent space to a manifold, then a positive symmetric form is called a Riemannian metric. Now let me comment that the analog of this theorem for non-positive forms is definitely false. For non-positive forms, the analogous theorem in quotes is false. And here's a significant example. Suppose we look at Lorentzian signature forms on the tangent space of some manifold. Well, if we had a form, then we could, a Lorentzian form, we could look at, say, some tangent vector whose norm squared is equal to -1, say, everywhere. Now that would mean we would have a nowhere vanishing vector field. That implies that there's a nowhere vanishing vector field. And we know that there's an obstruction for that. The obstruction is the Euler character. Okay? So if you have a manifold with a non-zero Euler character, you cannot put a non-degenerate Minkowski signature metric on it. Okay? So if space-time has a non-trivial Euler character, then you can't put a non-zero, you can't globally well-defined time. Okay, so, you know, in string theory, if you try and draw this diagram here, that world sheet has a non-trivial Euler character. There's no globally well-defined time slicing for your strings. Okay. Now, another, a nice little corollary, and then I'm almost done for today. A nice little corollary of this is that we have what's called a reduction of structure group. And I'll say what that means more formally in a subsequent lecture.
Professor,
Yeah.
I mean, do you want it to have a globally well-defined time?
Well, if you're doing physics.
I mean, but in GR, I mean, if you don't have a time like killing vector, I mean, that's possible, right?
No, but you can't even put a non-degenerate Lorentz signature metric. Okay? You can't even, it means, you know, in the equivalence principle, you say that locally you can find an inertial frame. What I'm saying is that, you know, you can't choose any metric such that locally you can choose coordinates such that it's an inertial frame. It's a little strange. Okay, so a corollary of this is the following theorem. Every real vector bundle admits trivializations with g beta alpha of x in ON, it's A, and every complex vector bundle admits trivializations with g beta alpha of x in UN. See, you choose a metric, and then you look at the frames which are orthonormal for that metric. And in those orthonormal frames, the transition functions have to be in ON or in UN. Now, a little exercise. Here's a good exercise for thinking about some of the things I've said. Now, you have to know a little cohomology to do this, but if you do, suppose that L over M is a holomorphic line bundle. Okay? And suppose that S is a globally defined holomorphic section of M. And suppose we choose a Hermitian metric, a positive Hermitian metric, on L. So what that means is that we have a globally well-defined C infinity function. I claim that a representative of the first Chern class is given by I over 2 pi dd bar of the log norm s squared. Very beautiful formula. Okay. So I'll let you think about that. It's a nice little formula. Okay, the very last thing I want to say for today is the following observation. I mentioned before that line bundles play a distinguished role. Remember, so a real line bundle is a one real dimensional vector space, vector bundle over a manifold, and a complex line bundle is a one complex dimensional vector bundle over a space. Now, line bundles form a group, which we could call the Picard group of our manifold M. Now, why is that? Ultimately, the reason is that if I tensor product over the R, over the reals, I get the reals, and if I tensor product complexes, I get the complexes. Okay? And moreover, if I take the dual space to the reals, that's canonically the reals, and the dual space of the complexes is complexes. So if I have two line bundles, L1 and L2. If those are two line bundles, and I take their tensor product, that is, again, a line bundle. You see, if the trivializations of L1 are these are one-by-one matrices, real and complex, according to what category we're talking about. So the tensor product is the product of these one-by-one matrices. Okay. And that's the transition function of L1 tensor L2. Okay? So you don't have this for vector bundles, right? If you have a vector bundle of rank n, and you take a tensor product with a vector bundle of rank m, you get another vector bundle of rank n plus m. So it doesn't close. You do have this tensor product, so you do have this ring structure. But here you have more. Actually, the line bundles form a group because L dual has G beta alpha of XL inverse as transition function. So L tensor L dual is isomorphic to the trivial bundle. Okay? So it's the multiplicative inverse under the tensor product operation. So that means the line bundles form an abelian group, the Picard group of M. And it can be interesting in some situations to talk about what is the Picard group of the manifold. All right, well, I got through about half of what I wanted to do today. So, Wednesday we will continue, and I'll begin by talking about some very special vector bundles, continuing some examples, that are called the tautological vector bundles over the Grassmannian. So going back to the Grassmannian and having a look at some very natural vector bundles of the